Hi everybody, sorry for the delay. I uploaded the latest version of the lab. I did some corrections, and now I will habilitate Octavio as a co-host. Yes, okay, and myself the other computer. Octavio, are you there?
Yes. Yes,
Okay.
just I'm here.
Okay. Okay. And now I have. Okay. So let's continue from where we stopped yesterday. I will share my screen on my laptop computer. Okay. Great. Can you see that?
Yes.
Okay. First, I would like to know if you have some questions from yesterday, some doubt about the lab. Were you able to run it? Everybody of you managed to install MATLAB and was able to run the labs, at least the solutions. Don't be shy.
I was able to run the solution on my PC, but I had real troubles in following the lesson.
Okay. In which sense that it was too fast, or it's just a matter of practice of playing with MATLAB and Simulink?
A bit both. I understood when you explained the process in constructing the solution, but I couldn't keep up on MATLAB.
Well, that's fine. That's fine. The important is that the practice that I gave you was just for you to play around a bit. But the importance is that you are able to replicate at home and understand the concepts and play around with the parameters. Now that you have the solutions, in essence, you will have possibility to change the parameters to do simulations and better understand the topics that explain the theory. So these labs are just to make you have a practical grasp of what is what was explained in the theoretical class. So don't be afraid. Use as an opportunity, as a tool for you to better understand.
If I may add, so yesterday I think that the purpose of Michele showing you how to build the blocks was not for him to follow precisely every step that he was taking, but rather to give you sort of a guide in case you were lost. So the idea is, well, I would suggest that you try to do the exercises yourselves, to reproduce, try to see how to solve each of the problems, and then once you have a solution, once you have a plot that you can see, you can compare it with the solution that we are providing, just to see how far and how close were you. And then the idea of Michele building the blocks during the lab, it's in case you are lost in at some specific point, and then you can ask a specific questions. So don't feel bad if you're not able to follow to construct, or rather try to pay attention to the details that Michele is showing at the moment when he's building the block.
Yes, correct, Octavio. So it takes I mean, I use MATLAB since more than 15 years, so it takes a while to get familiar with that, and so this is just a starting point for you to practice, in essence. So to continue, since we have only 1 hour or even less, I would continue solving the next exercises one by one, but without letting you practice, unless you're willing to do that. Just because we need to continue with the Python lab for the optional one. So let me know. These blocks are increasing or of increasing complexity. So in my opinion, it takes some time to do that, and you might not able to do that in 10-15 minutes. So I uploaded the updated PDF. I updated a bit, and the last time we were seeing a model of our motor plus load, and a model of the sensors, where we have a current sensor and the position encoder and the velocity sensor, which is the derivative of the position. We saw that the problem in the sensor model is that we have quantization, and the effect of quantization can be mitigated through the action of a filter at the price of a delay. Now, if we want to change the parameter of the filter, we increase the time constant of the filter, that is here. I don't know, let's say we want to do 10 times, so a 10 times slower filter. Again, we evaluate these new values for the filter that will recompute the beta and the P and beta V parameter of the position and velocity filter, respectively. So these are digital filter. And if we simulate, we see that the filtered version, that is the blue one, it's way less noisy than before. Before was kind of quite a big noise around, not as the original signal, which is the yellow one, but we start to see the delay of the action of the filter. So the ground truth is a red curve, while the filtered one is the blue one. So for a stronger filtering action, we will have as a price to pay a bigger delay. Now, what we want to do? We've seen that the load falls under the action of gravity. We have this curve, and we have 0 voltage here, but we have a current. We have a current that is non-zero due to the action of the back EMF. So the first step in our controller is to compensate the back EMF. And to compensate the back EMF, we take the filtered load speed We multiply by the gear ratio, N, to get the motor speed. And then we multiply by the speed constant, K. And of course, so why there is a minus sign here? Yeah, sorry. The back EMF was with a minus sign, so we want to subtract the back EMF. And if we do that, so we apply a voltage and that is 0, but we apply an input voltage that is subtracting the action of the back EMF. This, what we'll do, it will cancel out this feedback. So we cancel out, because we are summing something that is similar, the same as this, we'll cancel out this term by applying a voltage that is opposite. And if we simulate, again, we see that the load, it's, as you remember, since we compensate the back EMF, reduce the damping of the system, because the back EMF can be seen as a friction, as a damping. And so the loads start to oscillate more around the 0 position under the action of gravity. And if you look at the current, is small, but it's almost 0. Why is not exactly 0? Because we are doing not a perfect cancellation. So we are not doing a perfect cancellation because we are using the filtered load speed, which has a delay in the filter, which has quantization error. Let's see if we use the ground truth. If you use the load speed without, let's say, the original simulated speed, without passing through the filter model. And if we do so and simulate again, we can see that we are able to perfectly cancel the back EMF and have 0 current, because we have 0 voltage. Okay. Everything is clear till now? Then the next exercise is to do a current controller. So we want to do a current controller, for example, to do a gravity compensation. So we want to, we have the load starting in a 0.5 theta 0 initial position of 0.5 rads, and we want to apply the gravity current, the current that is able to compensate, is creating the torque that is compensating the effect of the gravity itself. So if we open the C3 sensor back EMF current, we get this. So first we compute from theta 0, we compute the gravity torque. So we do the same that we did to in our simulator in here, where we were computing the gravity torque this way. So it's theta 0 sine ml, that is the mass of the load, times gravity, times the length of the load divided by 2, that is the center of mass position, because it's so that we said that the load is density is uniform, so the center of mass is in the middle of the rod. And then we get what? We get a gravity torque, and if you want to get a current, we divide by the torque constant, and we get a current. Then this will be the reference current of our current controller. And now we need to design the current controller. So we have a reference current to track, we have a feedback current, and the exercise asks you to design a P controller, so a proportional controller based on the current error. So first we create a current error, subtracting the actual value of the current, which is the measured current from the sensor, from the reference one. And then we create, we design a proportional controller that is just a gain, okay? So the error times the gain, the KP gain, and this will be a voltage. So it's a voltage. That is, if you remember the class on the current control, is a voltage that is fed to the system. And on top of that, we add the back EMF compensation. But to design the current controller, we need to understand what is the value of this gain. And to do so, remember, we presented at the lecture on tuning PID controller a method that is called Ziegler-Nichols method, where you should have your system, right? And you should apply an open loop input. In this case, we have a voltage input for tuning. We cut the loop here. We have this switch. If we do like this, we get the input from here. If we do like this, we get the input from the controller. So for now, forget about the controller and just activate the input from this constant. So we give a step input, 1 volt to the system. And what we want to control? We want to control the current. So let's see the open loop response as Ziegler-Nichols asked us to do. First, we need to simulate. Simulation it's quite long because they're taking 4 seconds. Sorry, just a second. Because we kept the previous filter gains that we want to restore. So I just recall the initialization of the system. Okay. Now let's have a look to the initial response of the current, and we see here that we have an initial delay.
Did
right?
you put back the time constant that you changed, multiplied times 10? I don't remember.
So the time constant, I think I loaded again the things here.
Yeah, but you wanted to show that if you change the time constant of the...
Yeah, I reloaded the init.m, so I should... Ah, no, that's right.
Yeah.
I modified. Good point. Yeah, you spotted. So I just loaded, but with the wrong values. Now I run it. Oh, this is what I was expecting to see. You have a very long simulation time. So we wanna maybe consider just the first 0.5 seconds. Okay, then we look at the response here. And we get something around 1 millisecond. And you remember you need to get first the delay of the system, and then you need to get the intercept between this approximation, this tangent to the flexum that is here, and the intercept is around 1.3, 1. 29.3. And then the gains from one input to that is the steady state value. In essence, the gains is the steady state value divided by the input we gave. Now I don't understand why this is 1.1. Anyway, if we look like here, if you divide the steady state value by the input, you get this value, and theta, we said, is around 1 millisecond, and T1 is the intercept with the equilibrium point, is around 1.29, and if we compute the Ziegler-Nichols values, we can then compute, go to the table of the Ziegler-Nichols and get the proportional action that is around 0.33. And if we use this gain in the, we restore the controller, so we close the loop now with the P controller. We have a PI controller and a P controller, and we simulate. And we look at the current tracking, we see that the current is not going to the reference. So we should go to this reference, that is the reference needed to compensate for gravity at 0.5 rad, and it doesn't go. So this is a steady state error. And so this controller is not enough because it's not able to remove the steady state error. We can try to increase, like multiply by 3 times the proportional action to see if the steady state error reduces. Yeah, the steady state error is reduced, but it's never going to be 0. And this is because, you remember what is missing?
We should use the integral action.
Correct. We are missing an integral action. So keeping the same response parameter for Ziegler-Nichols from the response, we go to the table of the PI controller. Yeah, sorry, I think in the slides there is a typo. So the table for the PI controller. No, I corrected the typo. Yes, it was PD. That was wrong. So we go here and we get these two values. So we replace the TI variable with free theta and KP with this one. We evaluate this and we have to implement the PI controller. So how the PI controller is implemented is the proportional action. You remember, PI controller, proportional action times the error plus 1 over S, it is the integrator, times KP over TI. So KP is this, divided by TI. We are using this in this formulation, just the standard form. So this one, so these two terms are the PI. If you want the derivative, we also have this. But we sum this term with this term and we get our PI controller. Then we go back. This is the block we are using. We try to use that and simulate. And you will see now that the current is going to 0. To the tracking error steady state is going to 0, thanks to the integral action. So let's have a look to the load. What happened to the load, in your opinion? Do you think that we are able to reach to keep the position of the load constant at 0.5, which is our theta 0, with this approach. Let's see. So the load initially slightly go down, then it catches up and goes to 0.495. It's not really going to 0.5. So there is something here. There is something that, even though if we perfectly control the current, prevents the system to go to keep the state, the initial state that you had, even if we provide this. Why this? Because we have many non-idealities. We have sensor noise at the current level, the sensor velocity level, and then we also have the Coulomb friction. So if you remember, this is just an open loop controller for position, because we just have the model of our system, this is gravity. We say we want to have this position. We check what is the gravity current, and we give it as a feed forward without closing the loop on the position. So it is expected that you have an error in position. So what do we do to improve? We need to close the loop also in position. Therefore, we open the closed loop position PD. And the closed loop position PD is just our PI controller. Now we pack it. We used only that. We don't care much about the P controller anymore. And we implement a position PD controller. So to implement a position controller, we need to compute the control error, the position error. So this time we, instead of theta 0, we want to do things harder. We want to have the pendulum upright. So theta ref pi half. So 90 degrees upward. We say that 0 is downward. So a theta ref of pi half of 90 degrees, it's the pendulum positioned in an upward configuration. So this is the reference position, and we subtract the position of the load, the measured one. We have our sensor here that provides the position of the load, and we compute the control, the position error, sorry, for our controller. Then how the controller is done. We check again our slides. They are here. So we want a PD controller. PD controller means we have this. Okay, let's use, this time we want to use the parallel form. So let's check this first line here. We have the proportional action times the error. Yes, the proportional action. And this one should be summed up with what? With the derivative action. And the derivative action is KD times S times the error. But you remember that S is not realizable because of the fact that we have more zeros than poles. So we need to introduce a high frequency pole to make it realizable. You remember whatever we did here. So we replace the KDS with KDS over 1 plus tau S, where this is the tau of the high frequency pole. And we set this tau, how much? At high frequency. So this is the formula we were using. So to start with, I start with some gains like this. We don't want to use Ligon and Lycos this time. We want to do trial and error. So we have our reference of pi half. We have the proportional action. We have the derivative action gains. We set some values. We can compute from them the derivative high frequency of the pole for the derivative. And then we are summing the derivative with the proportional action, and we get our control action. And our control action is a reference for our current loop. So here we have the current loop, that is an inner loop, and in a cascade architecture we have an outer loop, which is a loop in position. Plus we have the feed-forward current. We have a feed-forward term that, you remember, is used to improve tracking. So now if we simulate this, and you look, so let's first look at the current loop. He's doing whatever it's asked to. Yes, there is some saturation, watch out. So this is the real current that cannot increase beyond the rated value, the nominal value, and this is the desired current. So, but at the steady state, there is a proper tracking of the current. While if we look at the position, we see that we are setting pi half, which is 1.57. It stands for 90 degrees in rads. And then the load starts from 0.5 initial state and tries to go to the reference, but there is a steady state error. And so again, there is a steady state error because we are using we have no integral action. We are using a PD controller. And what we try to do, as we did before, is to increase the value of the proportional action. To play around, because you remember in the lecture where we said what happens playing with the different gains, the proportional derivative one, we have different responses. So we said that increasing the proportional gain doesn't nullify the error, the steady state error, but reduces that. And actually it's true, the steady state error was reduced. But on the other half is increasing the overshoot and is going toward instability. How can we say that? We increase even more. We try to go to 2.6. And see, the overshoot is even bigger and there starts to be oscillation. The steady state error is still there. So we try to increase even more, 3.6. And you have more oscillation. I believe if I put 10, what is 6, the system can be unstable or not? What is your bet? What is your opinion?
Unstable.
Unstable, okay. Davide says unstable, somebody else says something else. It's just, I don't know, 10 euro bet. Let's see. Yeah, it's unstable. You see the oscillation are growing. You remember the definition of instability? State diverges from the equilibrium. And if I increase the simulation time to 10 seconds, for example, you will see that it becomes bigger and bigger. And this is very bad. Imagine your robot starting to swing like hell and kicking around people and machines. Is making a mess. So this is exactly what you don't want, instability from your controller. So we need to be careful. We just increase the proportional action. I mean, to be careful with that. Now let's try something else. Let's see how much important is the. So I go back to a value that I felt was the best one, which was 1.6. Sorry, I put again 2 seconds. Yeah, I didn't evaluate the other gains. I just changed the value. So I need to put in the memory and simulate again. Okay, this was the best response I got. And let's see how important is the feed forward. We said that the feed forward relieves the action of the controller in trying to tracking the reference. First, let's have a look to the control action. So our control action, I split into the feed forward term, which is the yellow part, which is around, sorry, this is a current. Well, all of these are current. We have a feed forward term, which is 2.1, 2.5 car amps. Then we have the proportional action, the blue one of the PD gain, which is here. It's 0 at the end. And we have the PD, the D action, the derivative action. It is very, very big at the beginning and then goes to 0. So if we remove the feed forward action and run again, let's have a look to the response. Wow, we have a big error here. And our controller, the proportional controller action, you remember, was around 0. Now has to take the lead, the effort that was previously provided by the feed forward action. So before, the feed forward current was providing, was helping the feedback controller, because was providing this current that is needed to keep to move the position to the reference. But now we don't have anymore that help, and so the feedback part of should take care of that with the proportional part in the specific. So whenever you have a feed forward, the outcome is that you can decrease the feedback controller gains. If you don't have the feed forward action, you would have to increase the feedback gains. So now let's try to increase, but then you remember that if you increase too much, the system can become unstable and the response deteriorates. So again, it's a tricky problem. So all this stuff that I explain you are helping in making a better controller. Then we still have a steady state error, you remember. So now we want to implement the integral action. So instead of PD controller, we now have a PID controller. And how the PID controller is implemented, again, it's implemented the same way. As before. So we have 1 over S, and this time we have the direct form. So we don't care about bigger and equals. I want to use the parallel form, not the standard form, which I like most. And I like most because I can directly tune the gain of the integral. And then we have all these three summed up to the current reference, and these are just output for plotting the control action. So now we evaluate these gains. This is, let's say, our KP PID controller, the KD of our PID controller, and the KI, the integral action of the PID controller. And this is the high frequency pole for derivative action realizability. We evaluate this, we simulate again. And we see this response. There is one big oscillations that this plateau, and then it goes to 0. So the integral action is doing its work. We can increase even further the integral action, but as I told you, you can get oscillations and longer settling time if you do that. This is what you happen if you give too much integral action. But why we have such a bad response, in your opinion? Let's see the current. Wow, current is doing nice, but at the beginning is again it's saturating. So maybe we are asking too much from our system. Let's try to pretend that we have a better motor. So let's try to increase 5 times the limits in the current, in the saturation of the current. And let's see how the system improves. We see here now there is no longer a saturation there. Let's look at the response. It's much nicer. So that bad response was due to the saturation of our actuation. So what we do, either we increase, we buy another motor, so we have better current rating and torque rating, or we need to accept a slower response. So we reduce the gains, the proportional gains, integral gains. We will have a slower response, but we cannot have both things. Okay? We cannot have both things with this kind of approach. That is a position PID loop and an inner current loop. These are the control actions. And again, we see that we have a very, very high, again, this is current. We have a very high derivative action. Beginning, this is the derivative action. We have an integral action. And the integral action will be non-zero at the end because it needs to compensate for the steady state error to make it 0, while the proportional action also is not 0. So what can we do now? Do you have a different idea? How can we improve this? We can improve this, for example, doing a cascade loop architecture. So putting another loop in the middle between the position and the current loop. So you have the current loop here, as before. We have a velocity loop. So this is the velocity controller that provides a reference for the current plus the feed-forward term here again. And out of that, the velocity controller receives reference from the position controller. So we have a position error, the position loop that is computing position error. We have a position controller that spits out a reference velocity. And this reference for the velocity, it's creating a velocity error that is given to the velocity controller. And this spits out a reference current. And the reference current is given to the as a reference to the current controller. So the idea is that we should have at least an integrator, to remove the steady state. We decide to put it at the position level. So we use a PD for the velocity controller and a PI for the position controller. If you look into them, you see that PD is the same as we implemented before. We have just a different name for the tau of a pole, and derivative gains and proportional gains. They have different names just to don't make a mess in the init script. And then if you look inside the position PI, you have different gains, KI pause for the integral part, KP pause for the proportional one. And now if you simulate this, we start again from the current tracking. Okay, the current is tracked, not so nice at the beginning, then it goes to steady state. Then we have the velocity is better tracked. You have the reference and the current just at the beginning, it's just a bit like that. And we have the position. Okay, wow. So you remember before the steady state was taking more than 2 seconds. Now it's a bit faster. We have less overshoot and zero steady state error. Now, as a last exercise, instead of a constant reference, we want to compute a time varying reference, so a trajectory, because, for example, we want to move our robot arm from one point to the other. So we need to give a reference position for the joint of the robot that is going from the actual position of the joint to another reference position. And to do so, we want to create a trajectory. How this trajectory looks like. Again, let's have a look to the instructions. We are now here, time varying reference tracking. And what, in your opinion, is better to do when you want to go from one point to another in the minimum amount of time in terms of velocity profile or acceleration? Do you want to start slow and accelerate and decelerate?
I think that we should accelerate to the maximum speed, then keep it, and then decelerate with the maximum deceleration we have.
Okay, so the maximum speed, we don't know what is the maximum speed, but let's say that you can achieve whatever speed. So you could accelerate for the first half of the trajectory at the maximum acceleration, that is, you remember, limited by the maximum torque you can provide from the actuator, and then decelerate at the maximum of your acceleration towards zero. So this will create something at the velocity level, a trapezoidal, triangular shape. But let's say that the range we need to do is very long, and we don't want to go too fast. So we accelerate for a certain time. Let's say for 1 second we accelerate, and we give the maximum acceleration, and the velocity will increase with a slope, for example, of 1 rad per second squared. So this is, let's say our maximum acceleration is 1 rad per second squared. Then we keep the velocity constant for 1 second, and then, so no acceleration, zero acceleration here, because we keep the velocity constant, and this means we have zero acceleration. And then we decrease, we create a negative acceleration at minus 1 rad per second that will drive the velocity to zero. And this for another 1 second. So for first second, we accelerate, keep constant for half second, and then for another second, we decelerate to zero. And we get something like a trapezoidal velocity profile. And then we set it, so this is theta ref, I will correct afterwards. We keep zero velocity. And so let's do that. We want to create this trajectory generation. So the first step in the next exercise is to create the trajectory generation. And to create the trajectory generation, we have, for example, this block here. So we have a selector that selects between 0, a selector that selects between 0 and 1. So whenever the time is bigger than 1, is smaller than 1, it gives 1 rad acceleration. Then if it is bigger than 1, it gives 0. Then here you go in this block. Whenever it's bigger than 1.5, it will start to decelerate, okay, giving -1 acceleration. And whenever the time becomes bigger than 2.5, it will provide 0 acceleration. And this is the acceleration that is something like as this shape, something like before positive, then 0, and then negative. The integral of this is the velocity reference, and the integral of the velocity is the position reference. So let's look, how do they look like? We just try to simulate them. And they look like this. So this is the acceleration reference. First 1 rad, then 0, then -1 rad over second squared. Then we have the velocity reference, that is a 1 rad slope, and then constant, and then down to 0. And this is the position. You remember the position. We start from the initial position, and we will accelerate, go constant velocity, and decelerate. And we will reach our endpoint, that is 2 rads. Okay, so we go from 0.5 rads to 2 rads. This is our joint reference. Then we now the important thing, you remember, with the feed forward, we have a feed forward term. You remember the slides on PID, that is time varying. So you remember the slides here, that if you have a time varying reference, acceleration, and so you have a time varying reference, which means that you have an acceleration and a velocity of the reference different than 0. So for the previous case, we are now, this is non-zero. Then you will have problems to drive the tracking error to 0. So what we want to do is to also add the feed forward action for the velocity and the acceleration. And to compute the feed forward, what we do for the velocity loop, we just give the reference velocity that we computed from the reference generation. while for the current loop, we need to compute the from the transfer function between velocity and current and velocity, we need to compute the current feed forward. And this is as this shape. So we have terms that depends on the acceleration, which means this is the reference torque that we need to give to drive the load at the reference acceleration, and then we divide this torque by k and we get the current, and this is the friction that we need to compensate to move at the reference velocity. And again, this friction torque bf tau f dot we divide for the motor constant and we get a current. Then we provide this sorry. So here we provide, we do this computation. So now we have 3 references. For the velocity reference, we said we just give the velocity feed forward from the velocity reference generation from the previous block. Then we multiply by bx divided by k, and we add the acceleration times jx divided by k, and we sum these two, plus we have also the gravity part, because the gravity is something that you want to compensate as well, and this is the current feed forward. Plus we have the back EMF compensation from the velocity reference that we are no longer doing from the actual value, but from the desired value. But this is the back EMF you can choose if using the actual value or desired reference value to do that. And these feed forward are given to the controllers, and we have the 3 controllers here in cascade. We have the first we have the possibility to activate or deactivate the feed forward terms, and we have the current PI controller, the velocity PD controller, and the position PI controller. And we have the feedback coming from the current, from the load speed, and from the load position. And this is the feed forward from the velocity that goes summing to the output of the position reference. So reference velocity plus feed forward velocity. Then we have the current reference that is coming from the velocity controller, plus the current feed forward, plus we have the back EMF compensation that is at voltage. And first, let's try to don't consider these feed forward references. So I just set this input to 0, that will nullify the feed forward terms, and I just simulate to see what I want to see, the position of the load. So we have the reference load position that we got from before from the reference generation, and we see that we have a tracking, we have a PID, so we have no error at the steady state, but we have some bad tracking during the transient. And you remember that the role of the feedback action, feed forward action that we will enable now is to remember the role of the feed forward action is to improve the tracking when you have a reference that is time varying. So let's try to simulate now with the feed forward action activated. And you can see that now the tracking is very good. So we are able, in this lab, we were able to see different implementation of the control. First, an inner loop controller, We have compensating the back EMF and doing gravity compensation. And we were trying to implement different kind of controllers. First, only a PD controller at the position level, then improving this with a PID position controller. We saw that there were big overshoots still. So we try another architecture, which was a cascade loop architecture with an inner current loop, an outer velocity loop, and an even outer position loop. And we were seeing that we had a massive improvement in the response, both in the speed and in the overshoot. And using this controller, we were trying to track not a constant reference, but a trajectory for the reference, which is a time-varying trajectory. And we saw that the feed-forward action was very important, also in that case, to improve the tracking during the transient. So if I have any other question, you can ask.
I've got a question about the optional part of
Yes.
this laboratory. When is the deadline?
The deadline is the exam day.
Oh, okay. Okay, thank you.
Okay, so if there is no other question, I give space to Octavio to start his lab on the Python tutorial. I hope you got the announcement to install the virtual machine. We also remembered yesterday, and you should use this virtual machine to follow and put in practice what Octavio is saying, and try, if you want, immediately the code it's presenting. You should also find, sorry about that, Octavio, I don't know if you put the slides online.
No, I didn't put them
Okay.
myself, but I was planning to put them after
No,
today's session.
I will put them now, such that the students can also follow with that. Sorry, we create a PDF quickly. You can start up and share.
So I was gonna say maybe we should take a 10-minute break.
Yeah. Let's do a break. In the meanwhile, I upload the Python lab. It's called L2 Python lab.
It's called L1 Python Lab because it was supposed to be first.
Now it became L2, so I changed it.
Yeah, that's fine. So shall we? Should we should reconvene in like 10 minutes? Okay.
Yeah.
Okay.
Fine.
Scusi, professore,
Sì?
sa per caso come riesco a ingrandire la finestra della macchina virtuale? Che adesso ce l'ho abbastanza piccola, è un po' scomodo.
Dovrebbe essere una cosa... Aspetti un attimo, eh. I settings della macchina virtuale sono stati fatti correttamente, come nelle istruzioni, tipo numero di processori, scheda memoria video,
Sì, sì, ho fatto tutto quanto.
e non si riesce a massimizzare la...
No, ho provato a guardare su internet, ci sono tipo dei pacchetti da installare, però me li dà come non trovati dando l'input sul terminale. Quindi non so se devo installare dei pacchetti direttamente nella macchina ospite oppure fare qualcosa direttamente nella macchina virtuale.
Scusi, non c'ero, state parlando che non potete fare la scheda grande della macchina virtuale?
Sì,
Ah, si deve... Ah, vi faccio vedere nel tutoriale se vuoi, quando
ok,
cominciamo.
perfetto. Cioè, è un problema che hai avuto anche te, Ottavio,
Sì,
sai?
sì, 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 lo
Ah,
avevo.
ottimo,
Sì,
perché a me non è mai successo.
sì, sì, sì. No, no, no. Adesso ne parlo.
Io ho un problema invece per quanto riguarda la password. Io non ho settato nessuna password, ma per scaricare PyCharm mi chiede una
È
password.
student.
Sì.
Ok, grazie.
Lo
Student
stesso
era
nome.
l'ho messa nelle istruzioni dell'annuncio perché non l'avevo inserita su Moodle. Mm.
Sì, anche io mi sono dimenticato. Okay, so 10 minutes have passed. So welcome to this Python introduction. Some of you were commenting during the break that you were having trouble with the virtual machine, specifically about the size of the window. So I will start by solving by showing you how I solved the issue, because I also had it. So give me 1 second. Okay, so I will start sharing my screen. Now some went away. Okay, give me a second. Share screen. Okay. Can you see my screen now?
Yes.
Yes.
Okay, so I'm gonna start the. So one thing is that if you manage to install the virtual machine, my config, because it detects the default language of the user. Mine is now in Spanish. So, but it should say new here. You click here, you create your own virtual machine. If you type Ubuntu, it actually suggests the name of the virtual machine, and then you type next. Usually I gave about 8 megabytes. It's not a problem. And then from here you select the file that we provided in the announcement that Michele suggested. So I'm going to create it because I already have it here. So I'm going to start the virtual machine. It takes a while. I'm really not sure why it takes so long to load. Maybe it's just because it was created with in an older version, because I recently made one like clean installation of Ubuntu, and it was a bit faster to load. Oh, maybe let me show you something before, because this actually changes performance quite a bit. So if you go to the configuration, you can actually select the number of processors that you're using. So I'm currently using 5 out of my 12 CPUs in the laptop that I'm using. So I did this, and now I'm using the virtual machine in Windows. But you can also install this in Linux and in Mac OS systems. So again, I'm going to start this. And then this is going to take a while. Oh, that's never happened before. So let's. I need to change the screen that I'm sharing, actually. Oh, give me 1 second. Yeah, now it's loading Ubuntu. In any case, I can already start showing you what to do. So here in English, it says devices. So to fix the problem of the size of the screen. And then here it says insert CD with guest additions. So once your system is loaded, you insert the CD with the guest additions. And you see here that the option, it's grayed out. Here it says dimension to the size of the guest. And once you insert that while your system it's running, it installs something inside of the virtual machine, and once this is installed, you reboot, and then this option becomes available to you. And I clicked twice. I had to click twice for it to get. I don't know if you try this. If you try this and it doesn't solve it, for me, then I had to install inside of the virtual machine a package. I think it's called VirtualBox. So let me do sudo apt update. For those who have problems with the password is just a student. We forgot to I forgot to put on the announcement before, and at the very beginning, Professor Foki forgot to put it in the initial announcement, but hopefully you are able to do that now.
And I updated the announcement with the password.
Okay. Here, when you do sudo apt update and this is stopped here at server dev, don't pay attention to this. And if you see errors related to this, don't pay attention to this. This is because we created the virtual machine inside our local server in IIT. So this tries to look for our own local server. Obviously, it's not going to find it because you're not connected to the internal server of IIT. But don't worry if you see errors related to server dev. So then the program that I was telling you to install, it's called VirtualBox guest additions-ISO. So if the previous thing of inserting the disk, so I'm just going to insert it so that you can see what happens. So here it's like basically as if you were inserting a disk into your machine, and then it asks you if you want to run it. I'm not going to run it now because I have already done it. And then it installs something, and then you need to reboot the machine. Like you need to reboot it like manually. So you click on machine, do reboot, and then and then when the virtual machine restarts, it should solve the problem. So I'm gonna eject this. And okay, now that I'm already on the virtual, then we just need to install the PyCharm. I'm gonna do a reverse search just to see what the command that I did.
Excuse me.
Yeah, tell me.
About the VirtualBox, it says file cannot be parsed or opened.
When you try to insert the disk?
Sudo apt install VirtualBox guest additions.
It gave you another. So did you do sudo apt update?
Yes.
So maybe we can talk about it either during a break, during the break, or at the end of the lab. Just so I can see exactly the error. Is that okay?
Okay.
Okay. So did anybody else had any problem different to the ones that I have already mentioned? Okay. Seems like you didn't. So now let me change the screen. Let's see if this works. Okay, good. Now you see my presentation, right? Okay. So I will start the tutorial just as a disclaimer, as I already mentioned. Actually, I would like to start with something else. Let me just to give you a bit of a preamble to the lab. So one of the main reasons why we decided to do this tutorial is that it's the results of this self-assessment form. So here you see the form that I'm talking about. So even though we saw that a lot of you have a good knowledge of the language. There are also some that still that have zero knowledge, or somebody that has he grades his knowledge to 1. So this is just to kind of level the field, and also this doesn't have to be something to stop you to do the exercises and the assignments during the lab sessions. So, and mainly this is because most of you we saw that are taking the masters in artificial intelligence, and as you might know, as you might already know, this one of the main languages using in machine learning, it's Python. And then we saw that also something interesting is that even though NumPy it's an essential key for scientific computing in Python, there's a high percentage of you that have not used Python, NumPy, sorry. And then there's also the fact of ROS. And then something interesting is that already 30% of you are using Linux-based systems, which is good to hear, because as time goes by, it becomes a standard in general. And we know that if you want to do research in general, or do like advanced tech applications, usually Unix-based systems are better. So let me again stop sharing this screen and then go back to the presentation. Okay, good. Back to the presentation. So a bit of background on why we decided to use Python. So over the past, what you see in the slide, it's the growing popularity of languages over the past 10 years. And these 3 languages that I chose, I generated this graphic using an open source application. And I chose to use C++, Java, and Python because those are 3 of the most widely used languages in robotics. And as you can see, the popularity of Python takes off with respect to the rest from approximately 2014. And as I just mentioned, this is not only with respect to these 2 languages that I'm showing, but it's with respect to all languages to all programming languages. So let's start with what is Python. So Python is a high-level open source. This is in red because this is very important. General purpose programming language. The fact that it's open source, it's key for research and for robotics research in general. Now that we're starting to see that robotics it's going into industry, this might change. But the fact that it has been open source forever, that Python has been open source for such a very long time, allowed a lot of researchers to develop robotics applications based on Python. It was released in the 1990s by Guido van Rossum. And in the past 10 years, it has gained a lot of popularity. And this is already available in the virtual machine that we provided for this course. So why has Python become so popular? The main reason is that it's simple to read and write, and this makes it an easy tool to learn and teach. And this is because the syntax of Python is closer to natural language, to the way we talk as people, right? With respect to other programming languages, not languages in general, because that's what we used to talk, but programming languages. Another reason is that it has been supported by very big tech companies like Google, Facebook, Amazon, and they have been on the forefront of developing important libraries, as we will see. It has a lot of community support due to the fact that it's open source. And because of this, it has many libraries. One of them is NumPy, which has become the standard to do scientific computing in Python and in general in data science. And then we have SciPy, we have Django, we have scikit-learn. There are a lot of libraries that have been developed in Python. And along with the fact that you have a lot of libraries, the fact that it has a large community support, it makes the documentation always up to date, always available. The growth of Python, it's also closely related to the fact to the growth of machine learning and data science. So for example, tools like TensorFlow, Keras, PyTorch, I put Keras twice, they started growing because Python was such an available tool. And then, for example, Google started developing their own tools on Python. And that's how TensorFlow was born. And then we have a chart. I would like to show you a chart in which we see how many times machine learning was searched from 2004 up to, I think I made this like 1 month ago. And we see that from 2014, it started again to take off. And then if we go back to our initial graphic, then we see that this roughly coincides with this point. So now that we talked about all of the advantages and all of the reasons why Python has been growing, so should we use it for everything? The short answer is no. And the main reason is that this is in between quotation marks. It's deemed as a slow language. And there are two main reasons, which I'm going to be explaining in an oversimplified fashion. Of course, there are more strong arguments to say this, but the first one is that Python is an interpreted language rather than compiled. For example, C or C++ are compiled languages. So what happens is that as the code is running, it interprets the instructions and runs them at the same time. So in contrast, for example, if you have an efficient compiler, it can just analyze your code and optimize it to execute like things like redundancies, or for example, like double calls or things like this. So having a compiler is in general more efficient in terms of computation time. And the other reason is that Python is dynamically typed. And this means that you don't need to declare variables before you use them. This is similar to how MATLAB does it. Or opposite to how, for example, you do in C++, that you need to specify every time you declare a variable, you need to specify the type. And this makes it faster to write because you don't need to think about the type that you're using most of the times. And Python will take care of this. But and this is makes it easier for us as programmers, but it makes it more slower to be executed by the computer. So this is key because in robotics, being able to run your code fast, and especially knowing how much time your code takes to be run is essential. And this is what we deem as a real-time safe coding problem. And then there's this good reading material if you want to go more in depth in why the reasons of Python being slow. So again, if we say that Python is not fast enough, let's say for all applications, why are we going to use it anyway? So as I said, Python code is easy to read and write, and because of this, it's very good for prototyping, and test new ideas. The problem, for example, when you're developing in C++, is that you need to write your code, right? And then if you want to, for example, when you're running your system in a framework such as ROS, then you need to compile it, run it, and then maybe your code compiles, but then it's very difficult to see if you have a weird behavior. It's very difficult to understand the variable. So the fact that Python is interpreted and is dynamically typed makes it easier to develop new ideas. It can be scaled easier with respect to other languages because it's easy, like it's easier to read. So for example, if you want to collaborate with someone, because its syntax is closer to not the way we speak, the way we talk, it's better for readability. It supports object-oriented programming. So on top of all of these advantages of using Python and its easiness, it's powerful enough to be able to program things in an object-oriented fashion. And then, although we saw in the self-assessment form that not a lot of you had experience in MATLAB or Octave, which is kind of an open source version of MATLAB, it's easy to jump from MATLAB to Python. Well, it's a lower learning curve. There are certain caveats to learning Python that you won't see in MATLAB, but still, it's an easy jump if you have already worked with MATLAB. And one important reason is that we will mainly be working in simulation, so we don't have to think about real time for the time being. But this is something important to keep in mind once you have the chance to implement your algorithms in a robot. So even though we have all of these problems, well, not problems, all of these situations with Python regarding real time, we still use Python in robotics. We still use Python in a almost a daily basis. So we deal with jumping from Python, at least in our lab, we do Python and C++ programming mostly. So where do we use this? So one of the main ideas, as I mentioned, is that you can implement ideas fast. So for example, you come up with a new algorithm and you don't want to compile, run it, verify the try to understand the variables, then correct the code, compile again, and run. So what you want to do is Python, and since it's interpreted, you run, you find an error, you don't have to recompile, you have debugger tools to see the values of the variables as you run the code. So it's easier to do this. Another application of Python in robotics is for code wrapping, and this is related to its readability, and these are called Python bindings. So basically, you can write a library in C or C++ that it's because they are faster. But if you want to make it easier to read or to implement, you can write a Python, wrap the library around a Python binding, and it's easier to understand, to read, to implement without sacrificing the speed of the application. Then, as I already mentioned, in machine learning applications in robotics, since the language that most of the researchers use in the machine learning community is Python, Python has made its way into robotics through machine learning as well. So for example, if TensorFlow and PyTorch are widely developed, and these libraries are growing a lot. Like PyTorch has updates every month to improve performance related to parallel computing operations in GPU. And we're starting to see a lot of applications where the GPU programming is starting to let's say get performances as languages such as C and C++, but not quite yet. But we are at a point like that. And then this is also used for non-real-time critical applications such as navigation and mapping, where so you don't use it in general to do control. So for example, if you want to move a joint, what we were seeing in the previous lab, we don't use Python in those applications because you need to do it because the time response of the system is really fast, and Python cannot provide this kind of fast behavior. So instead, we use Python for applications where you do navigation, mapping in general, because the update rates of this kind of systems are super slow, in the order of 5 Hertz, 10 Hertz, 20 Hertz. Whereas, for example, when you want to do the control that we were seeing in the previous lecture, it's about 1,000 hertz. So before this lab, as I already mentioned, you have installed, or at least try to install LocoSim. So if you try the virtual machine, it should already be installed there. So for now, you don't have to worry about it. Then we are going to try today to see if I'm going to tell you how to test if it is actually running. Also, you could have tested it natively on Ubuntu. The version that we're using is 16.04, but I understand that from Michele that you can also run it in 18.04. But just to avoid problems between different versioning of things, I would recommend to try it on Ubuntu 16, even though it's kind of old. At least it gives us the certainty of the things that we're doing, because it's the fact that it's old, it makes it more well established. And just as a test now, has somebody ever heard about Docker or containers in general? I guess not. Okay, so Docker, it's a similar technology. Well, containers are it's like containerized environments are it's a similar technology to virtual machines, but the nice thing about them is that you don't have to create a virtual kernel. You run it on your own kernel, and basically it's easier to use the resources of your own machine. So I made a Docker for this with the applications that we needed, a Docker container. So if you read about it after and you're interested in using it, it would be good for us as feedback, just to see how easy or difficult it is, and maybe we can think about it in the future to implement this. But just shoot me an email. I think I put my email in the previous announcement. If you are interested in learning how to use the Docker for this lab. The other thing is install the community version of PyCharm. Again, sorry for not. I guess that if you didn't guess that the password was the same as the user, you wouldn't have been able to install PyCharm. But the password, again, I repeat it, is student, as the same name as the user. And then, but if you already know Python, or you are used to a different tool, IDE, text editor, you can use as you prefer. But just keep in mind regarding this previous comment, I will be willing to help you. I know also other IDEs like Spider, Visual Studio Code, even a text editor, some text editor like Sublime, but it's gonna be harder because I'm testing this in PyCharm. So it might take a bit of time, but again, you're free to use it. I will help you, but just bear in mind that it might be more difficult and time consuming. If you have problems, send me an email or ask me during a break. I guess that today we're not going to have a break, but if you want to solve any problem, we can stay after the lecture, and then I can try to troubleshoot those issues. So let's talk about, now that I introduced PyCharm, let's talk about IDEs. So an IDE, it's a software to build applications that combines developer tools into a single graphical user interface. And the advantages of using an IDE is that it provides auto-completion. So for example, if you don't know, if you have an idea or don't remember exactly how a instruction, a command, like a built-in instruction is used, you can just try to remember in a word, and then usually IDEs suggest you the end of the word. It does variable linking, which is very good when you're trying to debug code. So this is very important. And again, debugging,
and what I mean here with debugging is being able to run your code piece by piece, and like dynamically while you're running the code, you can see the values of the variables, how are they changing. So it's easier to track errors, even if your code runs entirely. Sometimes you make a mistake. For example, you are stuck in a while loop because the condition is never met. These kind of debugging tools are very important when you are developing software. And in general, having an IDE, like a dedicated IDE for the language, makes code writing easy and efficient. So I set a dedicated IDE for the language because sometimes text editors, they also do autocompletion. You also can have variable linking, but a lot of these autocompletion features are based on machine learning rather than the language itself. So sometimes it's going to try to guess what you want to write, and most of the times it's going to be correct, but it's not based on the code that you're writing or on the language, but rather than on the patterns that you're following while writing a code. So again, in this tutorial, I'm going to be using PyCharm, and whenever we do the lab sessions, I will use PyCharm. So it's already in the virtual machine. Well, now I hope that it's already in the virtual machine. And why did I choose to use PyCharm? It's because I tried 3 or 4 alternatives: Spider, Visual Studio Code, just using a text editor. And for me, it was the easiest way to set a virtual environment that could be used along with ROS, which is the robot operating system, which is in what we're basing this lab. But you're free to use any alternative. There are many alternatives to program, and there are many that are multi-language. I personally like Visual Studio Code, but I think that again, the same thing that I said before. It's going to be harder to troubleshoot problems for us. So before we start, and probably we will, because we only have about 8 minutes. There's a bit of a disclaimer about the versions that we're going to be using on Python. There are many versions of Python on that you can use. So for you, there's 2.7, 3, 3.5, 3.9. The current version is Python 3.9. And these versions evolve really fast, both due to the fact that that the language is growing a lot, but also because it's open source, because it has a large community. The language, the version, I mean, this year they deprecated the last year the 2.7 was deprecated, and just at the beginning of this year 3.5 was also deprecated. So that's just to tell you how fast. C++ takes like 5 years to change version sometimes. But the problem is that older versions, as I mentioned, they are no longer maintained. However, a lot of applications still rely on older unmaintained versions, the ones that are deprecated. And unfortunately, this is very common in robotics. And one of the main reasons is that most of the software is developed in labs and not in companies. So you as a researcher, you are implementing something in the tools that you're familiar with, and then switching from one version to another takes time. And then let's say most of the people that do the new things are PhD students, which are worried about getting their degree, so they want to publish fast. So it is hard to have a good let's say coding ethics in terms of keeping you updated and also having good documentation, when you're also worried about publishing a paper. So just to explain to you that in our case, and just to justify that in our case, we're going to be using Python 2.7 because the main reason is that the dynamics library that we're using, which is actually the state of the art in dynamic simulation, which is called Pinocchio. It's written mostly on it. It's very well supported. Like the guys who developed it, can provide support mostly for Python 2.7, and they are just starting to migrate to Python 3.5. So this is why we're using 2.7. And it is important to keep this in mind, because if you want to move to more recent versions of Python, some libraries and built-in functions can change slightly. I will show some examples during the tutorial, but however, the overall essence of the language is the same. Okay, so a final piece of advice, maybe we can stop the tutorial here, and then we can resume it on the next lecture. The first of all is that this is a basic introduction, so I'm not going to go super deep in very advanced functions. I'm just going to give the basics that you need in order to understand the code that we're providing to you to do the lesson, to do the lab assignments. But Python and NumPy, which is the library that we're going to be using to do matrix computations and all of the required calculations that we need to develop our algorithms, they're always updated and they're easy to understand. I think that if you compare the document, let's say, if you compare the documentation of Python with the documentation of C++, you will find that it's way easier to understand Python, mainly because the nature of the language, because it's closer to the way we talk as humans. But then I'll share some useful resources, the official Python 2.7 documentation that we're going to be using. So, for example, if you read a function, a built-in word, something that you don't understand in the code, you can always refer to the documentation of Python 2.7. Then there's a wiki book on Python that is very, very well documented. And then there's also the official documentation of NumPy. Okay. So I would say, let's see what's next. Okay, I would say that it's good to stop here. If you have problems, you can stay now. We can try to troubleshoot them together. If not, let's continue the tutorial on Monday, and then see you then. I don't know if the professor has something else to say.
Yeah, so I wanted to maybe say that next week I won't be available to do the lecture. In case you finish, I'm sure you will finish on Monday, I think, both labs on Python. So we might skip the lecture of Tuesday. Anyway, we have Slack in terms of days before the end of the semesters, such that we can skip. We can do that without problems.
Maybe the better alternative could be because I don't think that it will take me more than 2 hours to do this. So as you prefer, we can either skip Monday or Tuesday. For me, it's not a problem.
Yeah, okay. If you think you might not need more than 2 hours, then we can skip Monday. Then we keep the 2 hours on Tuesday, and we go directly to the 6th after Eastern. When is Eastern? Let's see. It's 4th, yes. So after Eastern, it will be the next one if we skip the one of Monday. Anyway, yeah, we can announce this more precisely.
Yeah. So just to summarize and to make it clear, then Monday lecture, it won't happen. The next Monday's lecture, then Tuesday we'll have the Python tutorial. Again, if you feel that, so the slides are already available, you can go through them. So if you feel that it's too easy for you, you're not also not obliged to attend to the tutorial. This is just for the ones that don't have any previous knowledge on the language or very basic knowledge of the language. So feel free to note. There's no extra assignment in this tutorial, so it won't affect the chances for you to get the LODE. So just for you to be aware. So maybe without further ado, let's if somebody has questions on troubleshooting, just ask me, and then we can go through through how to solve them. For the rest, you can leave.
Yeah, I still couldn't change the resolution of the virtual machine.
Okay.
I did use the guest additions, but it still tell me that it is not possible. So
okay, so let's do something. I'm gonna stop sharing my screen, and then I will allow you to share yours, and I can see what's happening. Okay, let me try to do this. So yeah, I think you're already able to share your own screen. So if it could. Okay. So you still have the problem, right? So why first, I think that eject the disk. So right click on it, on the disk symbol on the yes, there, right click. Now right click, just to okay, that's fine. You can eject it in however you want. Yes, that's fine.
I already did this. I already ejected once to install it because the first time I didn't work.
Okay.
After I ejected and restarted the virtual machine, then I went here. I clicked this, and I run the script, and then still does not change the resolution.
Did you try installing guest additions?
Yes, I did.
Through the terminal.
Sorry?
Yeah, through the terminal. So just eject the disk in any case. Now go open a terminal and type sudo sudo, yes, apt install virtual box dash, so Tratino guest. Now try tab, so the tab key, just to see if it auto completes.
Oh, doesn't do anything.
Okay, so can you do something? So can you do Control-C just to do another one? Can you do ping space google.com? Okay, you are connected to the internet. So Control-C to stop it. So now do sudo apt update. Oh, I see what it was not auto-completed. Install is missing an L.
Oh.
Yeah, it went to a previous command. And yeah, now you have a lot of possibilities. So you need to at least give it a clue. So type N, yeah. No, now you're running the same command twice.
Sorry?
Yeah, you're running sudo apt install, sudo apt install. So just after install. delete sudo, go back. No, there, install with double L space VirtualBox guest, Tratino guest. Try tab now. Okay, type an A. Yeah, additions. No, just the letter A, and tap. Okay, now install this. Enter. Now the password student. Okay, enter. Yeah.
So slow.
Yeah. Did you change the number of processors that you're using?
Yes, I did.
How many did you assign?
Here.
Yes, sistema. Processore. Okay, yeah, you're using 4, so it should be fine.
I will have those, so
Yeah. Maybe it's your internet connection. I think it's the internet connection. But in any case, this is also a big package. Something failed. Can you put the disk again and try to install it again? So the dispositivi and then yes. Try run now just to see what happens. Put the password. Okay. So when you tried it the first time, were the messages in that terminal that appeared the same?
yes, this is not different from.
Okay, I mean the only different part from what you're doing to with respect to what I did, it's this error messages. So try install it again and see if we got rid of those error messages.
Shouldn't I restart the?
I just want to see if because it says in one of the errors that I don't know where I read that it failed to mount the disk. Unit failed to resolve. I think in one of the upper parts. I mean, okay, let's try to restart and see if the behavior repeats.
Oh. All right, but I have to.
Okay, if you don't have time, that's fine. We can. So next lab session, we can. If you want, we can meet a bit earlier, and then we can try to solve this problem. If you don't manage, otherwise, I will post my solution, what worked for me, because I installed it in 2 different computers, and then I installed it using the virtual machine that was provided. And in the other computer, I used a different virtual machine, and the solution, it's a bit different, but it just involved installing these virtual guest editions. Otherwise, I can also send you more resources where I find other solutions.
Another solution, Octavio, is that we can update the virtual machine VD file with the PyCharm and everything is missing, such that they don't have to do that.
But the problem is not that PyCharm is not installed. The problem is that by default, the aspect ratio of Ubuntu, it's this one, and then you need to. Well, I don't know if you have already. I tried having this already installed and putting it in another machine, and I had to do the same thing again. I had to install this guest additions thing. So I will try to troubleshoot this, and by if I find a solution before the next lecture, I will post the announcement. Otherwise, just let me know in advance if you want to meet earlier, and then we can try to troubleshoot this together. Okay.
All right.
Okay. Good. Anybody else has another question or problem not related to this that we couldn't solve?
How do I stop the screen sharing?
There's a button on top. If you put your cursor in the
Oh.
middle of the screen on top, it says stop share.
Yeah. All right.
Okay.
I have to go. So.
Yeah, no worries. So if nobody else has questions, then I will also take my leave, and I will post the announcements. Anything to say, Michele?
No.
Okay, then
Okay.
see you next week.
See you after Easter. Anyway, I might sure the next session, but I want teaching and Octavio will teach. And have a nice evening for today. I closed down the recording. Bye.
Okay, bye.